Okay, so get comfortable, get your blanket, put your phone down somewhere you can still hear this. Maybe turn the lights down a little bit. Because what we're going to do tonight is walk through the entire process of building a quantum computer, and we are going to take our time with every single part of it. There's no rush here. We're going to go slow. We're going to be thorough. And by the time we're done, you're either going to understand quantum computing better than most people on the planet, or you're going to be deeply asleep. And honestly, both of those outcomes are completely fine. Also, as you can see, since Bob listened to too much math, he is a calculator now, and he hopes you can still accept him. But on a serious note, I will link the community post explaining this change in the comments. As always, all the sources we used before creating this script are in the description. And let's just start at the very beginning, which means we have to start with a problem. The problem is this. Regular computers, the ones sitting in your pocket and on your desk and in your laptop, they work by pushing electricity through billions of tiny switches called transistors. Each one of those transistors is either on or off. That's it. That's the whole thing. On is a 1, off is a 0. And by arranging enormous chains of 1s and 0s together, you can represent any kind of information at all. A photo, a song, a word, your entire bank account, all of it is just 1s and 0s stacked up in the right order. And transistors can flip between those states incredibly fast, billions of times per second. So the computer can do billions of these simple on-off operations every single second, and out comes something useful. The problem is that some problems are just so complicated that even doing billions of operations per second isn't fast enough. There are certain problems in chemistry, for instance, where you want to simulate how a molecule behaves, how its electrons move around and interact with each other. And the thing is, electrons don't really behave like tiny little balls moving around on fixed tracks. They behave according to the rules of quantum mechanics, which means they exist in a kind of blurry cloud of possibilities all at the same time. And the way you actually describe what they're doing mathematically requires you to track all those possibilities simultaneously. And as you add more and more electrons to your simulation, the amount of information you need to track grows exponentially. Add 1 more electron and you double the amount of work. Add 2 more electrons and you quadruple it. Add 30 electrons and you're dealing with numbers so enormous that you'd need more memory than there are atoms in the observable universe just to store the state of the system. And that's just for 30 electrons. Real drug molecules, real materials, real chemical processes involve hundreds or thousands of electrons. Your classical computer simply cannot hold all of that information. It cannot hold the problem in its head at the same time. It has to take shortcuts and approximations, and sometimes those approximations are fine, but sometimes they miss something important and you just never find the material you were looking for, or the drug that might have worked, or the answer to the problem. So that's where the idea of a quantum computer comes from. The insight which Richard Feynman articulated back in 1981 at a conference at MIT was something like this. If nature is quantum mechanical at the bottom, maybe you should simulate it with a quantum mechanical system. Instead of pretending that electrons our classical particles and doing an approximation. What if your computer was itself made of quantum objects that could be in superposition and become entangled with each other, and so could naturally represent all those simultaneous possibilities without any approximation at all? That was the idea. And it took a few decades for people to work out the details of how you might actually build such a thing. And today, we're going to walk through those details together, slowly and carefully, all the way from the raw materials to a working machine. And the first question we have to answer is, what are we actually going to build out of? There are several different physical platforms you can use to make a quantum computer. You could use individual ions, which are just atoms with an electron missing, so they carry a charge and you can hold them in place with electric fields. You could use photons, which are particles of light, and you can encode quantum information in the polarization of a photon. You could use electrons trapped in tiny quantum dots in silicon. You could use something exotic called topological qubits that are still mostly theoretical. Or you could use what most of the big companies like Google and IBM are using, which are superconducting circuits. We're going to go with superconducting circuits. And the reason we're going with superconducting circuits is that they're the most mature platform right now. They've been developing for over 2 decades. There's an enormous amount of published research about how to make them and how to control them. And the companies that have built the largest quantum processors in the world, from Google's Willow chip to IBM's Condor processor, they all use this approach. So, if you want to understand how the state of the art actually works, superconducting qubits are where you want to focus. It's worth a brief moment to understand why the other platforms are interesting, even though we're not going to go into them in depth, because the comparison helps clarify what's actually hard about building quantum computers in general. Trapped ion qubits used by companies like IonQ and Quantinuum have some genuinely compelling properties. Individual calcium or white terbium ions are held in place inside a vacuum chamber by a carefully shaped electromagnetic trap called a Paul trap, which uses oscillating electric fields to keep the charged ions suspended in space without touching any walls. The qubit states are encoded in the electronic or hyperfine energy levels of these ions. The ions can be manipulated using extremely precise laser beams. Because they're identical atoms in vacuum, every trapped ion qubit is inherently the same, with no fabrication variation, and coherence times for trapped ions can be extraordinarily long, up to minutes in some cases, compared to microseconds for superconducting qubits. The problem with trapped ions is that they're slow. A 2-qubit gate between trapped ions takes microseconds to milliseconds compared to tens of nanoseconds for superconducting qubits. This is because the entangling gate has to go via the shared vibrational modes of the ion string, which have low frequencies. You also need to do a lot of laser and vacuum engineering to make these systems work, and scaling them up to hundreds or thousands of ions in a single trap while maintaining the ability to address each one individually with lasers is a significant engineering challenge. Different companies are exploring different approaches. like shuttling ions between different zones of a more complex trap structure, or using photonic links to connect multiple smaller traps into a larger network. Photonic qubits, used by companies like SeqQuantum and QuicksQuantum, can in principle operate at room temperature, since they don't require the extreme cooling that superconducting qubits do. Light doesn't interact with its environment the way electrons do, so photons can propagate through optical fibers for long distances without losing their quantum state. And there's a huge existing industry of photonic components from telecommunications that you can leverage. The challenge is that photons are really hard to make interact with each other. Two photons will just pass right through each other in a waveguide without doing anything. Getting them to interact in a way that creates the entanglement needed for a 2-qubit gate requires very clever tricks involving special nonlinear materials or specially engineered optical circuits and probabilistic measurement-induced entanglement, and these tricks are inherently noisy or inefficient. Achieving fault tolerance with photonic qubits requires enormous amounts of overhead. And then there are silicon spin qubits, which encode quantum information in the spin states of single electrons or atomic nuclei in silicon devices that look somewhat like very small transistors. The appeal is that silicon fabrication technology is extremely well developed. After decades of the semiconductor industry, the qubit footprint can be incredibly small, enabling very dense arrays, and the coherence times can be long. The challenges are that the coupling between spin qubits is quite short range, requiring careful design of coupling mechanisms, and that reading out the spin state requires measuring very tiny currents, which places extreme demands on the electronics. But there's been rapid recent progress in silicon spin qubits, and several groups have now demonstrated 2-qubit gates with very high fidelity. All of this is to say that when we focus on superconducting qubits, we're not saying the other platforms are wrong. We're saying that for the purpose of understanding how most of the current state-of-the-art quantum computers actually work, superconducting is where the most fully developed engineering exists today. The other reason we're going with superconducting circuits is that the physics of how they work is genuinely beautiful. Once you understand what a Josephson junction is, and why it creates an anharmonic oscillator, and why that anharmonicity is the thing that makes a qubit possible in the first place, everything else kind of snaps into place. And we will get to all of that. But first, we need to talk about the factory you need to build this stuff in. So let's start at the very beginning of the physical process, which is the clean room. A clean room is a room where the air is filtered so thoroughly that there are almost no particles floating in it at all. And the reason you need this is that the structures you're trying to build are incredibly small. The features on a superconducting chip are on the order of micrometers, which is millionths of a meter, and the Josephson junctions, which are the most important components, have features down around 100 nanometers, which is 100 millionths of a millimeter, which is several times smaller than some viruses. And if you have a dust particle landing on your chip during fabrication, that dust particle is probably bigger than the feature you're trying to make. It will ruin the junction, it will short out the circuit, and all your work is gone. So the clean room has these enormous air handling units in the ceiling that are constantly pumping filtered air down through the room, and out through perforated floors. The air is classified by the number of particles above a certain size per cubic meter. A standard outside environment might have millions of particles per cubic meter. A clean room for semiconductor work might be class 100, meaning there are at most 100 particles per cubic meter that are bigger than half a micrometer across. And in the really sensitive areas around the electron beam lithography systems, you want to be as close to class 10 as you can get. Everyone who goes into the clean room has to wear a bunny suit. This is a full-body garment made of tightly woven material that doesn't shed fibers, plus gloves, booties, a hood, and a face mask. You have to go through an air shower before you enter, which blows jets of clean air over you to knock off any particles that are clinging to the outside of your suit. And inside the room, you move slowly and smoothly because turbulent movement stirs up particles. You don't make sudden gestures. You don't walk fast. You kind of float around in there, which is actually quite meditative once you get used to it. The clean room also needs very careful humidity and temperature control. Humidity matters because water vapor can cause chemicals to behave unpredictably during the etching and deposition processes. Temperature matters because thermal expansion of the equipment can throw off the precision of your lithography. So the HVAC systems in these facilities are incredibly sophisticated, maintaining temperature to within a fraction of a degree and humidity to within 1% or 2%. And once you're inside the clean room, you're ready to start actually making your chip. The starting point is a wafer. In our case, because we're making superconducting qubits, we're going to use a silicon wafer or a sapphire wafer. Sapphire is actually preferable for many high-performance qubit designs because it has lower losses at microwave frequencies, which matters a lot for qubit coherence. And we'll come back to what coherence means in a while. But let's say we're using a silicon wafer for now, because silicon is more widely available and the processes for working with it are extremely well understood. The wafer comes from a supplier as a disk of highly pure single crystal silicon. Typical size for research purposes is 100 millimeters or 150 millimeters in diameter, which is 4 or 6 inches across. The silicon has to be incredibly pure, like 9 nines of purity, meaning 99.999999% pure silicon, because any impurities can scatter microwave photons and cause losses in your resonators and qubits. The crystal orientation of the silicon also matters and is specified when you order the wafer. You typically want wafers with what's called a 100 orientation, meaning the crystal planes run parallel to the surface in a specific way. When the wafer arrives, it gets cleaned very thoroughly. This is called RCA cleaning, named after the Radio Corporation of America, where it was developed back in the 1960s, which is kind of funny given that we're using it for 21st century quantum computing. The RCA clean involves a sequence of chemical baths. First, you do what's called an organic clean, using a mixture of hydrogen peroxide and ammonium hydroxide heated up to about 70 degrees Celsius, which removes organic contaminants like skin oils and solvents. Then you do a quick dip in diluted hydrofluoric acid, which strips off the native oxide layer on the silicon surface and leaves you with a fresh hydrogen-terminated silicon surface. Then you do what's called an ionic clean using hydrogen peroxide and hydrochloric acid, which removes any metallic contamination. And then you rinse everything very thoroughly with ultra pure water, which is water so pure that it barely conducts electricity at all. The reason you're so obsessive about surface cleanliness is that the surfaces and interfaces are where a lot of the loss in superconducting qubits comes from. There was a whole period in the history of the field, from roughly 2010 to 2020, where people kept trying to improve qubit coherence times and kept running into a kind of wall. And it turned out that a big part of the problem was microscopic defects at surfaces, things like two-level system defects in surface oxides, tiny little quantum systems that could absorb microwave photons and then release them back in a random way, spreading errors through the qubit. So all that careful cleaning isn't just fastidiousness, it directly translates into better quantum computers. Now, let's talk about the actual structure we're trying to make on the chip. A superconducting quantum processor is basically a microwave circuit. If you could zoom in on one of these chips and look at it, you'd see a network of metal wires and pads sitting on the surface of the silicon or sapphire, looking a bit like a very complicated printed circuit board, scaled down by a factor of 1,000. There are long, winding resonators that look like coiled or straight metal traces. There are coupling elements connecting things together. There are the qubit structures themselves. And underneath all of those metal structures, where they sit on the substrate, is where you most need to worry about those surface defects. The primary metal we're going to use for the main circuit elements is either niobium or aluminum or tantalum. Niobium is a classic choice and has been used in superconducting electronics for decades. It has a superconducting transition temperature of about 9.2 Kelvin, which is quite convenient because it means you can cool it with liquid helium and get superconductivity well before you hit your operating temperature. Aluminum has a lower transition temperature of about 1.2 Kelvin, but is also widely used and is great for making Josephson junctions. Tantalum is newer to the quantum computing scene, but has been generating a lot of excitement recently because qubits made with tantalum tend to have longer coherence times, with some recent results showing coherence times approaching half a millisecond, which is a big deal. So let's say we're going to use niobium for the main circuit and aluminum for the Josephson junctions, which is a very common combination. The first step in making the circuit is to deposit a thin film of niobium onto the cleaned wafer. We do this using a process called sputtering. You put the wafer inside the vacuum chamber, pump the chamber down to a really good vacuum, and then you introduce a very small amount of argon gas. You have a target of pure niobium on one side of the chamber. You apply a high voltage, which ionizes the argon gas and creates a plasma. The argon ions in the plasma get accelerated toward the niobium target, and they smash into it, knocking out niobium atoms in the process. Those niobium atoms fly across the chamber and land on the wafer, building up a thin film. You control the thickness of the film by controlling how long you run the process. For most qubit applications, you want a niobium film somewhere between 100 and 300 nanometers thick. The quality of this niobium film matters a lot. You want it to be as pure as possible, with the right crystal structure and with as few defects as possible. The sputtering process needs to be tuned carefully to get this right. You control things like the argon pressure, the power applied to the plasma, the temperature of the substrate during deposition, and the distance between the target and the wafer. Getting all of these parameters dialed in is one of those things that sounds simple but takes months of experimentation and practice. After you have your niobium film, you need to pattern it into the actual circuit shapes. And this is where photolithography comes in. Photolithography is the same basic process that's been used to make microelectronics since the 1960s. You coat the wafer with a light-sensitive polymer called photoresist. You expose it to light through a mask, which is a glass plate with the circuit pattern on it in chrome. Where the light hits the resist, it either strengthens or weakens it depending on whether you're using positive or negative tone resist. Then you develop the resist in a chemical developer which removes the weakened parts and leaves you with a pattern of resist on the wafer that matches your circuit design. And then you edge the metal away everywhere the resist isn't protecting it, using either a liquid chemical edge or a dry plasma edge. The dry plasma edge is more common for niobium because niobium doesn't dissolve well in most wet chemicals. You put the patterned wafer into another plasma system, this time with reactive gases like chlorine or sulfur hexafluoride or a combination of gases, and the reactive plasma species chemically attack the niobium and convert it to volatile compounds that get pumped away. The parts of the niobium that are covered by the resist don't get etched. And so when you strip the resist away afterward, you're left with a niobium circuit pattern on your silicon wafer. This part of the process defines all the big features: the resonators, the ground plane, the wiring, the coupling elements, the big capacitor pads of the qubits. And the lithography for these features can be done with a standard UV photolithography system because the minimum feature size is around a micrometer or larger, which is well within what photolithography can handle. But now we get to the tricky part, which is making the Josephson junctions. And this is where we need to switch to electron beam lithography because the junctions are much smaller than what UV light can pattern. Let me tell you what a Josephson junction actually is, because it's the heart of the whole thing. It's what makes superconducting qubits fundamentally different from just a regular superconducting circuit. Brian Josephson was a graduate student at Cambridge in the 1960s when he worked out theoretically that if you take two superconductors and separate them with a very thin barrier of insulating material, something strange would happen. Quantum mechanically, the electrons in a superconductor don't behave like individual electrons. Instead, they pair up into things called Cooper pairs, which are pairs of electrons bound together by a phonon-mediated interaction, first described by Bardeen, Cooper, and Schrieffer in the 1950s. Cooper pairs are bosons, They don't have to obey the Pauli exclusion principle, and so they all condense into the same quantum state, which is what gives you the superconducting behavior. You get a macroscopic quantum state, a single quantum wave function that describes all the Cooper pairs in the whole piece of metal at once. When you put two superconductors next to each other with a thin insulating barrier between them, the wave functions of the Cooper pairs on each side leak into the barrier a little bit. And if the barrier is thin enough, which means on the order of 1 to 2 nanometers, the wave functions from the two sides actually overlap. And Josephson realized that this means Cooper pairs can tunnel through the barrier without resistance, even when there's no voltage applied. This is called the DC Josephson effect, and it was experimentally verified shortly after Josephson predicted it. Josephson won the Nobel Prize for this in 1973. The other thing that happens, which is called the AC Josephson effect, is that if you apply a voltage across the junction, you get an oscillating supercurrent. The frequency of the oscillation depends on the voltage, with a ratio of about 483 gigahertz per millivolt. This means Josephson junctions are essentially very precise frequency to voltage converters, and they're used in incredibly sensitive magnetometers called squids, among other things. But what we care about for quantum computing is something slightly different. We care about the nonlinearity of the Josephson junction. Here's the thing about a regular LC circuit, which is just an inductor and a capacitor. If you put charge on it, it oscillates between having charge on the capacitor and current flowing through the inductor back and forth, just like a pendulum. And if you think about the quantum mechanics of this oscillation, you get equally spaced energy levels. The energy of the ground state is some value. The first excited state is higher by a fixed amount. The second excited state is higher by exactly the same fixed amount again, and so on forever. This equal spacing is a problem for making a qubit, because a qubit is a two-level system. You want your system to have a ground state and an excited state, and then nothing else you care about. But if the energy levels are equally spaced, every microwave pulse you send to drive the transition from ground to first excited state will also drive the transition from first excited state to second excited state, because they cost exactly the same amount of energy. So your quantum information leaks out into higher levels and gets messed up. What the Josephson junction does is introduce a nonlinearity into the inductance of the circuit. A regular inductor has an inductance that doesn't depend on the current flowing through it. But the Josephson junction has an inductance that depends on the current, because the relationship between current and phase in the junction is not linear. It goes like a sine function. And this nonlinear inductance shifts the energy levels, so they're no longer equally spaced. The first excited state is a certain energy above the ground state, and the second excited state is a bit less than twice as far above the first excited state. So there's a gap in the spectrum called the anharmonicity, and if you tune your microwave pulses to hit exactly the frequency corresponding to the ground to first excited transition, they won't drive the first to second transition, because that transition is at a slightly different frequency. And now you have a two-level system you can actually control. Now you have a qubit. The specific design of qubit that everyone uses now is called a transmon. The transmon was invented at Yale by a team including Jens Koch, Jay Gambetta, and Rob Scholkopf back in 2007. The key innovation of the transmon is that it uses a very large capacitance shunted across the Josephson junction. This has the effect of making the qubit insensitive to fluctuations in the charge on the junction, which is a major source of noise in earlier qubit designs. The price you pay is that the anharmonicity of the transmon is relatively small, typically around 200 to 300 megahertz, which means you have to be a bit careful about how fast you drive gates so you don't accidentally excite higher levels. But the improvement in coherence from not being charge sensitive is worth this trade-off. A typical transmon consists of one or two Josephson junctions shunted by a large capacitor. The capacitor, in a planar design, looks like two big rectangular or circular metal pads sitting side by side on the chip, separated by a gap. They're connected together at one end by the Josephson junction. The whole thing is usually surrounded by a ground plane of niobium, which provides electromagnetic shielding, and the qubit is coupled to a microwave resonator for readout and control. So how do you actually make the Josephson junction? The most common technique is called double angle evaporation, and it was developed largely by Michel Devoret and colleagues in the 80s and 90s. The process goes like this. First, you define a pattern in the electron beam. Resist using electron beam lithography. The pattern has a very specific shape called a Manhattan junction or a bridge junction, where two strips of resist cross each other, with one of them having an undercut profile. The undercut is created by using a bilayer resist system. The bottom layer of resist is more sensitive to the electron beam, so when you develop it, the bottom of the structure has slightly wider opening than the top, leaving a little shelf or bridge of resist that's not connected to the main body. You put this patterned wafer into an electron beam evaporator. This is a vacuum chamber where you melt aluminum using a focused electron beam, and the evaporated aluminum atoms fly out and coat the wafer. For the first evaporation, you tilt the wafer at an angle, maybe 30 degrees to one side. Aluminum coats the wafer at an angle, going under the resist bridge in one direction. Then you oxidize the aluminum in a controlled way by letting a small amount of oxygen into the chamber. This forms the thin aluminum oxide tunnel barrier, which is the insulating layer in the junction. You control the thickness of this oxide layer and hence the tunneling strength of the junction by controlling the oxygen pressure and the time you expose the aluminum to oxygen. Finally, you tilt the wafer to the other angle and do a second aluminum evaporation. This second aluminum film overlaps with the first film in the area under the resist bridge, and the overlap region with the oxide barrier sandwiched in between is your Josephson junction. Then you strip the resist, which lifts off the aluminum everywhere except the junction area, leaving you with a tiny aluminum Josephson junction. The junction area is typically on the order of 1/10 of a square micrometer to about 1 square micrometer, and the oxide barrier is somewhere between 1 and 2 nanometers thick. You cannot see it with the naked eye. You can barely see it with a regular optical microscope. You need a scanning electron microscope to get a good look at the junction. And the thing that's crazy about this is that the properties of your qubit, specifically its resonance frequency and its anharmonicity, are determined largely by the critical current of this junction, which is in turn determined by the resistance of the tunnel barrier, which is in turn determined by the area of the junction and the thickness and quality of the aluminum oxide layer. So tiny variations in the junction size or tiny fluctuations in the oxidation process translate directly into variations in qubit frequency from one chip to the next and from one qubit to the next on the same chip. This is actually one of the biggest challenges in scaling up superconducting quantum processors. If you want 100 qubits on a chip, and each qubit needs to have a specific frequency that's different from the frequencies of its neighbors to avoid crosstalk, you need all those junctions to be fabricated with very high precision. And with the double angle evaporation technique, getting that kind of reproducibility is genuinely hard. A lot of current research is focused on either better fabrication methods or on using laser annealing after fabrication to fine-tune the frequency of each qubit individually. There was actually a really interesting paper published a few years ago where researchers used laser annealing to tune frequencies across a 65-qubit processor with a precision of about 18.5 megahertz, which is pretty remarkable given that the qubits have frequencies in the range of 4 to 6 gigahertz. The idea is that annealing the aluminum junction slightly changes its structure and resistance, which shifts the qubit frequency by a predictable and controllable amount. It's a bit like tuning a piano string by heating it slightly. Now, the reason people have switched to tantalum in recent years is really interesting and is actually a story about surfaces. It turns out that when you make a transmon with niobium capacitor pads, the niobium surface naturally grows a native oxide layer in air, niobium pentoxide, and this oxide layer contains what are called two-level systems, or TLS defects. Two-level systems are tiny quantum mechanical entities embedded in amorphous materials. They have a ground state and an excited state, just like a qubit, and they sit at frequencies in the microwave range. And this is bad because your qubit is also at a frequency in the microwave range, and if one of these TLS defects happens to be sitting right at your qubit frequency, it acts like a tiny trap that can absorb the energy from your qubit and then re-emit it at a random time, causing the qubit to decay. Even TLS defects that aren't exactly at your frequency can cause dephasing through a dispersive interaction. The reason tantalum helps is that the alpha phase of tantalum, which is the crystalline body-centered cubic form rather than the tetragonal beta phase, has a surface oxide that forms much more slowly and has far fewer of these TLS defects. The first paper demonstrating the advantage of tantalum came out of Princeton's De Leon group in collaboration with Hauck's group in 2020, published in Nature Communications, and it showed coherence times above 300 microseconds. This was a factor of roughly 3 to 5 improvement over what people were getting with niobium at the same time. And follow-up work has since pushed T 1 times up toward 500 microseconds using tantalum with dry etching processes. The fabrication of tantalum qubits is somewhat more involved than niobium because tantalum is harder to etch cleanly. Niobium can be etched with fluorine-based plasmas like SF6 or CF4, which are fairly standard. Tantalum is more resistant to these, and getting a clean, smooth etch of tantalum without leaving residue or damaging the substrate beneath requires careful optimization of the etch chemistry and plasma conditions. But the community has now largely solved these challenges, and tantalum is becoming the material of choice for high coherence transmon qubits. There's also ongoing work on the substrate side. It turns out the substrate matters a lot too, not just the metal. Even a perfect piece of niobium or tantalum sitting on a silicon wafer will have loss contributions from the metal substrate interface, where the silicon surface isn't perfectly crystalline and where there can be oxide and contamination layers. Sapphire substrates have been shown to have lower microwave losses than silicon in some configurations, which is why many high-performance qubit groups use sapphire even though it's more expensive and harder to work with. And researchers at various institutions are actively working on surface treatments like high temperature annealing in carefully controlled gas environments that can clean up these interfaces and reduce TLS loss. So now we have a chip with niobium circuits and aluminum Josephson junctions sitting on a silicon or sapphire wafer. Let's think about what else needs to be on this chip. Each qubit needs a readout resonator. The readout resonator is a superconducting microwave resonator, which is basically a short section of transmission line that's cut to a quarter wavelength or half wavelength at a specific microwave frequency, typically somewhere between 5 and 8 gigahertz. When the qubit is in its ground state, it has one effect on the resonator frequency, and when the qubit is in its excited state, it has a slightly different effect. This is called the dispersive coupling regime, where the qubit and resonator are coupled but not so strongly that they're constantly exchanging excitations. By sending a probe microwave signal at the resonator frequency and measuring the phase or amplitude of the reflected or transmitted signal, you can determine whether the qubit is in ground or excited state. This is called dispersive readout, and it's the most common qubit readout technique. The coupling between the qubit and its readout resonator is controlled by the capacitance between them. You want enough coupling to make a fast, accurate readout, but not so much coupling that the resonator causes the qubit to decay faster than it otherwise would, through a process called the Purcell effect. Managing the Purcell effect often involves adding another resonator called a Purcell filter between the readout resonator and the output line, which lets you have fast readout without too much qubit decay. Each qubit also needs a control line, which is a transmission line that brings microwave pulses to the qubit to drive gate operations. And if you're using tunable qubits, which have a squid loop instead of a single junction, and can have their frequency adjusted by applying a magnetic flux, you also need a flux bias line for each qubit. The way two qubits interact with each other is through capacitive or inductive coupling between them, either directly or via a coupling resonator that sits between them. By controlling the qubit frequencies and the drive pulses, you can turn on and off the effective coupling between qubits, which is how you implement two qubit gates. And then all of these lines, the control lines, the readout lines, the flux lines, the coupling elements, they all have to be laid out on the chip in a way that fits everything in the available space without causing crosstalk between elements that aren't supposed to talk to each other. This is the chip design problem, and it's done using microwave electromagnetic simulation software that can model how signals propagate through the circuit and how the different elements interact. People spend months designing a processor layout before they ever go into the clean room. Once the design is done and the chip is fabricated, we have a little piece of silicon or sapphire, maybe a centimeter on a side, with this beautiful dense network of superconducting metal structures on it. You can hold it in your fingers. You can look at it. It doesn't look like much. And here is where the problem really starts, because this chip is useless at room temperature. At room temperature, the niobium and aluminum are not superconducting. Niobium becomes superconducting at 9.2 Kelvin, which is 9.2 degrees above absolute zero, which is negative 264 degrees Celsius. Aluminum's superconducting transition is at 1.2 Kelvin, and even if the metal were superconducting, the qubit quantum states would immediately be destroyed by thermal fluctuations. At room temperature, thermal energy is on the order of 25 millielectron volts. The energy splitting of a transmon qubit operating at 5 GHz is around 20 microelectron volts, which is more than 1,000 times smaller than the thermal energy. Thermal photons at room temperature would constantly be banging into the qubit and scrambling its state. To actually run the qubit, you need to cool it down to around 10 to 20 millikelvin, which is 10 to 20 thousandths of a Kelvin above absolute zero. To put that in perspective, the cosmic microwave background radiation, which is the afterglow of the Big Bang, is at 2.7 Kelvin. Your qubit needs to be colder than the background temperature of the entire universe by a factor of about 150. To do this, you need a dilution refrigerator. A dilution refrigerator is one of the most remarkable pieces of engineering in the world. It's this stainless steel cylinder, usually about 1 meter in diameter and 2 meters tall, hung from the ceiling on vibration isolating supports and surrounded by multiple layers of radiation shielding. The inside looks a bit like an elaborate chandelier, with multiple circular metal plates hanging one below the other, connected by tubes and wires, and with the experimental payload at the very bottom. The whole thing gets evacuated to a high vacuum and then cooled in stages. The outer vacuum shell is at room temperature, around 300 Kelvin. Inside, that is a first stage cooled by a pulse tube cryocooler, a mechanical refrigeration device, down to about 40 Kelvin. This provides the first big drop in temperature and intercepts the radiative heat load from the warm outer walls. Then there's another pulse tube cooling stage that gets you down to about 4 Kelvin. These pulse tubes work by compressing and expanding helium gas in a way that pumps heat from cold to warm, and they're closed cycle systems, meaning you don't need to keep adding liquid helium. But getting below about 4 Kelvin is where things get interesting, because you can't just use more mechanical compression. You need a different mechanism, and this is where the dilution unit comes in. The dilution unit is based on a completely remarkable quantum mechanical phenomenon involving two isotopes of helium. Ordinary helium, helium-4, has 2 protons and 2 neutrons in its nucleus. Helium-3 is a rarer isotope with 2 protons and only 1 neutron. And these 2 isotopes have very different quantum mechanical behavior at low temperatures. Helium-4 is a boson, so it can undergo Bose-Einstein condensation and becomes a superfluid below 2.17 Kelvin. Helium-3 is a fermion, so it can't condense in the same way, and it stays as a normal fluid down to very low temperatures. When you mix helium-3 and helium-4 together and cool them below about 870 millikelvin, something remarkable happens. The mixture separates into 2 phases, just like oil and water separating, except in this case, it's not about chemical polarity, it's about quantum statistics. You get a helium-3 rich concentrated phase and a dilute phase that's mostly helium-4 with a bit of helium-3 dissolved in it. And crucially, as you approach absolute zero, the dilute phase doesn't become pure helium-4. It maintains a concentration of about 6.6% helium-3 dissolved in it, all the way down to absolute zero. This is because helium-3 atoms actually have lower energy when they're dissolved in the helium-4 superfluid than when they're in a pure helium-3 liquid, because they can interact with the superfluid phonon modes in an energetically favorable way. What this means is that if you have the boundary between these 2 phases, and you can pump helium-3 out of the dilute phase by continuously evaporating it and pumping it away, more helium-3 atoms will spontaneously cross the phase boundary from the concentrated phase into the dilute phase to maintain that 6.6% equilibrium concentration. And crucially, this crossing of the phase boundary requires energy, just like evaporating a liquid requires energy. This energy comes from the thermal motion of the surrounding liquid, so the surrounding liquid cools down. This is essentially a refrigeration cycle based on the phase boundary between 2 quantum fluids, and it can cool things down to well below 10 millikelvin with no moving parts at the cold stage, which is important because moving parts generate vibrations that would disturb the qubits. The coolest thing about dilution refrigerators is that they are fundamentally limited by quantum mechanics. The cooling power depends on the temperature cubed. So the colder you get, the less cooling power you have, and you can never get all the way to absolute zero. You can get to 5 millikelvin, you can maybe squeeze to 3 or 4 millikelvin, but there's a fundamental floor that you approach but never reach. Most quantum computers operate at around 15 millikelvin, which provides a comfortable margin above the floor while keeping thermal excitations of the qubits negligibly small. Dilution refrigerators are not cheap. A research-grade dilution fridge from companies like Bluefors or Oxford Instruments costs somewhere between $500,000 and $1.5 million. They also consume around 5 to 10 kilowatts of electrical power to run the room temperature, compressors, and pumping systems, and they take several days to cool down from room temperature. You don't just turn them on and off. You turn them on and leave them running continuously, doing maintenance and loading new samples without warming the whole thing up. The process of cooling down is itself carefully managed. You start with the pulse tubes running, which over the course of maybe 24 hours gets you down to around 4 Kelvin. Then You start the dilution unit by condensing helium-3 and helium-4 into the mixing chamber. This takes another 12 to 24 hours. And then you slowly descend through temperatures, watching the thermometers at each stage drop, watching the mixing chamber temperature slowly approach 15 millikelvin. And you take data on the chip as you go to make sure nothing went wrong with the thermal connections and wiring. Okay, so now you have a chip inside a dilution refrigerator sitting at 15 millikelvin. Now what? The chip doesn't do anything by itself. You need to be able to send signals to it and receive signals from it. And this is where things get really complicated, because you're trying to send microwave signals into a box that's at 15 millikelvin from electronics that are at room temperature. And the problem is that those room temperature electronics generate a lot of thermal noise. And if you just run a wire directly from your room temperature signal generator into the dilution fridge and down to the qubit, you'll pump enormous amounts of heat into the cold stage and warm the whole thing up. And even if you didn't warm it up, the thermal noise on that wire would be more than enough to destroy the qubit state. So you need a very sophisticated wiring strategy to get signals into and out of the refrigerator without dumping heat into the cold stage. The way it works is that you have carefully engineered coaxial cables running from the room temperature electronics down through each of the temperature stages. At each stage, the cables are thermally anchored to that stage, meaning they're clamped to the metal plates at that temperature so that the cable conducts heat away at the warmest possible point rather than dumping it into the coldest stage. The cables at the lower stages are made of materials with very low thermal conductivity, like stainless steel or superconducting NBTI niobium titanium alloy cables, which have essentially no electrical resistance, so they don't generate resistive heating, and which have low thermal conductivity. For the input lines, the ones carrying signals from room temperature down to the qubit, you also need to add attenuation at each stage. Attenuation is just a component that absorbs some of the signal, reduces its amplitude, and crucially, the noise floor of a signal generator is related to the physical temperature of the source. If you attenuate the signal at a cold stage, you're effectively replacing the noisy room temperature noise on the line with a signal whose noise corresponds to the temperature of the cold stage. So you do staged attenuation. Maybe you have 20 decibels of attenuation at the 4 Kelvin stage, another 20 decibels at the mixing chamber, and so on. By the time the signal reaches the qubit, it's been attenuated by enough that the noise floor corresponds to a temperature of about 40 millikelvin or less, which is cold enough that it doesn't disturb the qubit. Of course, you also have to apply more power at the input to compensate for the attenuation, which you do at room temperature, and the net result is a clean, cold signal arriving at the chip. For the output lines, the ones carrying the readout signals from the chip back up to room temperature, you have a different challenge. The readout signal coming off the chip is extremely weak, only a few microwave photons worth of power. And as that signal travels up the output line through the progressively warmer stages, the room temperature amplifiers at the top have noise that would completely overwhelm this tiny signal before you could measure it. So you need amplifiers that are as cold as possible, as close to the chip as possible. The most common approach is to use a HEMT, high electron mobility transistor amplifier at the 4 Kelvin stage. HEMTs are semiconductor amplifiers that work well at low temperatures and have low noise. With a good HEMT, you might add only a few noise photons equivalent worth of noise to the signal. But even a few noise photons can cause significant readout errors if your signal is also only a few photons. The ultimate solution is to use a quantum-limited amplifier, which is an amplifier that adds the minimum possible noise allowed by quantum mechanics. The most common quantum-limited amplifier for superconducting qubit systems is called a traveling wave parametric amplifier, or a Josephson parametric amplifier. These use Josephson junctions to do amplification in a way that adds as little noise as possible. A Josephson parametric amplifier can add less than half a noise photon to the signal, which is as good as physics allows. These amplifiers sit at the mixing chamber stage, right next to the chip. There's also another extremely important component that needs to go in the output line, which is a circulator. A circulator is a 3-port microwave device that passes signals around in one direction only. So, a signal coming in from the qubit goes to the amplifier, but any noise generated by the amplifier coming back toward the qubit gets redirected to a cold load and absorbed. This prevents the amplifier noise from reaching the qubit. Circulators for quantum computing applications are superconducting devices that rely on the non-reciprocal properties of ferrimagnetic materials like yttrium iron garnet in a static magnetic field. They work extremely well, but they're bulky and they do require a small static magnetic field, which needs to be carefully shielded so it doesn't affect nearby qubits. There's a lot of ongoing research into on-chip circulators that would be much more compact and easier to integrate. So now you have this whole stack of stuff. The chip at the bottom of the fridge, surrounded by attenuators and amplifiers and circulators and carefully thermally anchored cables going up through all the temperature stages to room temperature electronics at the top. The room temperature electronics for a modern superconducting quantum computer are themselves quite complex. You need arbitrary waveform generators that can produce microwave pulses with very specific shapes, phases, and frequencies. The pulses are typically on the order of tens of nanoseconds long. They need to be generated with phase coherence across all the qubits, meaning the phases of the pulses for different qubits all need to be synchronized to a common reference clock. The reference clock is usually a very stable microwave synthesizer or a direct digital synthesizer locked to a rubidium atomic clock standard to ensure long-term stability. You also need analog to digital converters on the output side to sample the returning readout signals fast enough to capture the qubit state information. And you need a real-time digital controller that can process the measurement results and decide in real time what pulses to apply next, which is essential for things like quantum error correction, where you measure certain qubits, process the results, and then apply correction pulses within a few microseconds. All of this control electronics adds up to racks and racks of equipment, easily costing hundreds of thousands of dollars per qubit if you're not careful. One of the big practical challenges in scaling quantum computers is that the classical control electronics scale with the number of qubits. So if you have 1,000 qubits, you potentially need thousands of signal generators and thousands of cables running into the fridge. Companies are working very hard on the problem of how to multiplex signals, how to run classical electronics at cryogenic temperatures inside the fridge to reduce the number of cables needed, and how to come up with fundamentally different approaches to control electronics that don't scale so badly. But let's step back from all of this engineering and think about what happens when we actually turn the thing on and try to make the qubits do something. The first thing you do when you've cooled down a new chip is characterization. You don't just immediately try to run a quantum algorithm. You spend days, sometimes weeks, carefully measuring every qubit and every resonator to understand exactly what you've made. You start by finding the resonator frequencies. You do this by sweeping a microwave tone across a range of frequencies, maybe from 4 GHz to 8 GHz, and looking at the transmission through the chip. Wherever there's a resonator, you'll see a dip in the transmission spectrum at that resonator's resonance frequency. From the width of the dip, you can measure the quality factor of the resonator, which tells you how much loss there is in the resonator. Then you find each qubit. The qubits don't show up directly in transmission in the same way as the resonators, because the qubits are only coupled to the readout resonators, not directly to the main through line. Instead, you use the fact that when a qubit is in its ground state, it shifts the readout resonator frequency by one amount, and when it's in its excited state, it shifts it by a different amount. By sending in a weak probe tone at the resonator frequency and watching how the response changes when you apply a qubit drive tone, you can find the qubit frequency. The qubit frequency for a typical transmon is somewhere between 4 and 6 GHz. You sweep a second tone across that range while probing the resonator, and when you hit the qubit frequency, you see the resonator response change. That's your qubit. Once you know the qubit frequency, you want to measure its coherence properties. The two main coherence times people measure are called T1 and T2. T1 is the energy relaxation time. It tells you how long the qubit stays in its excited state before spontaneously decaying back to the ground state by emitting a microwave photon. You measure it by applying a pi pulse to the qubit, which is a pulse that flips the qubit from ground to excited state, then waiting for a variable time and then measuring the qubit state. You plot the probability of finding the qubit in the excited state as a function of wait time, and you get an exponential decay. The time constant of that decay is T1. T2 is the dephasing time. It tells you how long the phase of the qubit's quantum state stays coherent. You measure it by applying a pi/2 pulse, which puts the qubit into an equal superposition of ground and excited state, letting it evolve for a variable time, and then applying another pi/2 pulse and measuring. A Ramsey experiment, which is what this is called, gives you oscillations in the measurement probability that decay with a time constant called T2 star. There's also a related measurement called a spin echo that gives you T2, which is longer than T2 star because the echo cancels out slow drift in the qubit frequency. For state-of-the-art transmon qubits in 2025, you might expect T 1 times somewhere between 100 microseconds and 500 microseconds, and t 2 times of similar duration. These numbers have improved by something like 5 orders of magnitude since the first superconducting qubits were made in the late 90s, when coherence times were barely a nanosecond. The improvements have come from better materials, better fabrication, better shielding, better filtering of electromagnetic interference, better engineering of the qubit geometry to minimize coupling to loss mechanisms, and a gradually improving theoretical understanding of what limits the coherence in the first place. The coherence time is ultimately what limits the number of gate operations you can perform on a qubit before the quantum information is lost. A gate operation takes somewhere between 20 and a few hundred nanoseconds, depending on the gate type and how fast you drive it. If your T1 is 200 microseconds and a gate takes 40 nanoseconds, you can do about 5,000 gate operations before the qubit is likely to have decayed. That's your quantum volume budget from just the T1 limit, and it's one of the key figures of merit for the quality of your qubits. After characterizing the coherence times, you calibrate the gate operations. The basic single qubit gates are rotations of the qubit state on the Bloch sphere. The Bloch sphere is a geometric way of representing a qubit state. The North Pole represents the ground state. The South Pole represents the excited state, and any point on the surface of the sphere represents some superposition of ground and excited states. A rotation around the x-axis by 180 degrees is called an x-gate, and it flips the qubit from ground to excited state or vice versa. A rotation by 90 degrees around x is called an x2 gate. Rotations around the y-axis are y and y2 gates, and so on. To implement an x-gate, you send a microwave pulse at the qubit frequency with a specific amplitude, duration, and phase. The phase of the pulse determines which axis you're rotating around. The area under the pulse envelope, which is roughly amplitude times duration, determines the rotation angle. Calibrating these gates means carefully adjusting the pulse parameters to make sure you're getting exactly the right rotation angle and not accidentally driving any higher level transitions. The calibration process involves running something called randomized benchmarking, which is a clever statistical technique where you apply random sequences of gates and measure the output. By varying the length of the sequences and looking at how the error probability grows with sequence length, you can extract the average error per gate. A good transmon qubit can achieve single qubit gate fidelities of 99.9% or better, meaning on average only 1 in 1,000 gate operations goes wrong. 2 qubit gates are harder and typically have higher error rates. The most common 2 qubit gate for fixed frequency transmons is the cross resonance gate, also called the CX gate or C0 gate in some implementations. The idea is that when you drive one qubit, called the control qubit, at the frequency of the other qubit, called the target qubit, through the coupling bus resonator, the microwave field that reaches the target qubit has a component that depends on the state of the control qubit. This state-dependent drive is the nonlinear effect that creates the entanglement between the 2 qubits. By applying the right pulse at the right frequency for the right duration, You can implement a CNOT gate where the target qubit gets flipped if and only if the control qubit is in the excited state. Calibrating a cross-resonance gate involves characterizing the strengths of a bunch of different coupling terms, applying correction pulses called echoes to cancel out unwanted terms, and then optimizing the pulse shape to maximize the gate fidelity of state-of-the-art 2-qubit gate fidelities for superconducting qubits are around 99 to 99.5%. Getting from 99% to 99.5% is a huge amount of work and is the focus of enormous research effort. You might be wondering why we care so much about gate fidelities, and the answer is quantum error correction, which is the next major topic we need to discuss, and which is really the core of what makes a large-scale, practically useful quantum computer actually work. But before we go there, let's spend a bit more time on the measurement side, because readout fidelity is just as important as gate fidelity and deserves more attention. When you send a probe tone into the readout resonator, you get a response signal back in the dispersive regime. The resonator is detuned from the qubit by a frequency gap called delta, and the coupling between them shifts the resonator frequency by a small amount called key when the qubit is in the excited state. Key is typically on the order of 1 to 10 megahertz. So, the resonator frequency when the qubit is in ground state is F, R, and when the qubit is in the excited state, it's F, R plus or minus key. If you send a probe tone at F, R and measure the phase of the reflected signal, you'll get one phase when the qubit is in ground state and a slightly different phase when it's in the excited state. The challenge is that chi is small relative to the resonator line width kappa in many designs, which means the two phases are close together and hard to distinguish. You want chi to be large relative to kappa for a fast, high-fidelity readout. But if you make the coupling too strong, you get what's called the Purcell effect, where the qubit can decay by emitting a photon into the resonator and then out through the readout line. Even when you're not actively measuring, this increases the qubit decay rate and shortens T1. The standard solution, as mentioned, is a Purcell filter, which is an additional microwave circuit element that blocks the qubit frequency signal from reaching the output line while still allowing the resonator frequency signal through. This lets you have a fast resonator line width for fast readout while keeping the qubit isolated from the output line at the qubit frequency. Purcell filters are now essentially standard in high-performance transmon designs. The actual measurement process involves sending a readout pulse, which is a short burst of microwave at the resonator frequency, for somewhere between 100 nanoseconds and a few microseconds, depending on the readout speed you're going for. The reflected or transmitted signal is amplified by the parametric amplifier in the HEMT, then demodulated at room temperature to extract the amplitude and phase. You take the in-phase and quadrature components of the demodulated signal and you plot them on a two-dimensional plane. Two clusters of points will appear, one for when the qubit was in the ground state and one for when it was in the excited state. The separation between the clusters, divided by the spread within each cluster, gives you the signal-to-noise ratio of the measurement. For a high-fidelity single-shot readout, you want those two clusters to be as well separated as possible. State-of-the-art readout fidelities for transmon qubits are above 99% for single-shot measurements, meaning if you measure the qubit once, you'll get the right answer 99 times out of 100. This is important for quantum error correction because you need high fidelity ancilla measurements to reliably detect errors. A readout error in the syndrome measurement can propagate through the decoding algorithm and cause logical errors. One thing that makes readout tricky is that measurement itself disturbs the qubit. When you send a readout pulse into the resonator, photons bounce around in the resonator and have a small probability of causing the qubit to flip through a process called measurement-induced state transitions. If you make the readout pulse too strong to get a faster measurement, you increase this back-action effect and degrade the qubit state. There's an optimal readout power that balances speed against this disturbance. Finding this optimal operating point is part of the calibration process. There's also a subtlety about what happens to the qubit after the measurement. The act of measuring the qubit and finding it in the excited state doesn't necessarily leave it in the excited state. Residual photons in the resonator after the readout pulse has been applied can continue to interact with the qubit and cause additional transitions. To avoid this, you typically add a reset step at the beginning of each experiment, where you cool the resonator down by driving it and then waiting for it to ring down, ensuring you start from a well-defined state. Resetting the qubit itself is another important operation. The simplest approach is to just wait for T1 and let the qubit decay to the ground state naturally. But if T1 is 100 microseconds, this means you're adding 100 microseconds of dead time between experiments, which slows down your data collection dramatically. Active reset schemes use fast feedback to reset the qubit much faster. You measure the qubit, and if you find it in the excited state, you apply a pi pulse to flip it back to the ground state. With a fast measurement and fast feedback, you can reset the qubit in a few microseconds instead of hundreds of microseconds. The thing is, even with T1 times of hundreds of microseconds and gate fidelities of 99.9%, a circuit with any serious algorithmic depth is going to accumulate errors. If you need to run a quantum algorithm that requires 1,000,000 gate operations, and each one has a 1 in 1,000 chance of going wrong, the probability that your computation completes without any error at all is approximately 0. You're going to have errors. In classical computing, this problem is solved by the extreme reliability of transistors, which have error rates closer to 1 in 10 to the 15th, and by error-correcting codes for storage and transmission. But in quantum computing, the error rates of physical qubits are nowhere near good enough to run deep circuits without correction, and making the physical hardware reliable enough to not need correction may simply be impossible, because no matter how good your qubits are, thermal fluctuations and quantum vacuum fluctuations will still cause errors. So the solution, which was worked out theoretically in the late 90s by Peter Shor, Andrew Steen, Alexei Kitaev, and many others, is quantum error correction. The idea is to encode one logical qubit into many physical qubits in a way that spreads the quantum information around, so that if one or a few of the physical qubits suffer errors, you can detect and correct those errors without actually measuring the quantum information directly. And that last part, without actually measuring the quantum information directly, is what makes quantum error correction so mind-bending. In classical computing, you can just look at a bit to see if it's been flipped. In quantum computing, looking at a qubit collapses its quantum state. If you measure a qubit in superposition to see if it's been flipped, you destroy the superposition and get back a classical 0 or 1. So you can't just copy the state onto multiple qubits and do a majority vote the way you do in classical error correction. The solution is a beautiful insight called syndrome measurement. Instead of measuring the data qubits directly, you introduce a second set of qubits called ancilla qubits or measure qubits. You entangle these ancilla qubits with the data qubits in a very specific way, such that each ancilla qubit becomes sensitive to whether a specific combination of data qubits has a specific parity relationship. The ancilla qubit, when measured, tells you whether a certain pattern of errors has occurred among the data qubits without revealing anything about the actual values of the data qubits. This is the syndrome measurement. By looking at the pattern of syndromes across many ancilla qubits, you can usually figure out what error occurred and where, and you can apply a correction. The key insight is that you're measuring a property of the errors without measuring the quantum information itself. The most widely used quantum error correcting code for superconducting qubits right now is the surface code, which was inspired by topological concepts in physics developed by Alexei Kitaev in the late 90s and early 2000s. In a surface code, you arrange your qubits in a two-dimensional checkerboard pattern. The data qubits sit on the vertices of the checkerboard, and ancilla qubits sit in the centers of the squares. The ancilla qubits in alternating squares measure the X-type parity of their neighboring data qubits, and the ancilla qubits in the other alternating squares measure the Z-type parity. You cycle through measuring all the ancilla qubits over and over again, and the pattern of where parity violations show up tells you where errors are occurring. The surface code has a very nice property called a threshold. If the physical qubit error rate is below a certain threshold, roughly around 1%, then making the code bigger, meaning adding more physical qubits to the encoding, makes the logical qubit better and better. If you start with 17 physical qubits in a distance, 3 surface code, 9 data qubits, and 8 measure qubits, you get 1 logical qubit with a substantially lower error rate than any individual physical qubit. If you upgrade to 49 physical qubits in a distance, 5 code, 25 data qubits, and 24 measure qubits, you get an even better logical qubit. If you go to 97 physical qubits in a distance, 7 code, better still. Google demonstrated this scaling behavior in 2 major papers. First, in 2023, they showed that a distance 5 surface code outperformed an ensemble of smaller distance 3 codes, which was the first experimental demonstration that error correction could actually improve with increasing qubit number. Then, in late 2024, they went further and showed that their distance 7 code, using 101 physical qubits on their Willow processor, had an error rate that was suppressed by a factor of about 2 compared to the distance 5 code. That is, every time they increased the code distance by 2, the logical error rate was cut roughly in half. This means you can scale up to get as small a logical error rate as you need by just making the code bigger. The practical implication of this is enormous but also daunting. If you want to run, say, Shor's algorithm to factor a large number and break RSA encryption, you need logical error rates of something like 1 in a million or 1 in 10 million per gate operation. To achieve that level of error suppression with the surface code, you might need each logical qubit to be encoded in 500 or 1,000 physical qubits. And a computation like factoring a 2048-bit RSA key might require a few thousand logical qubits. Multiply that out and you're looking at millions of physical qubits. Running that computation would require a quantum computer that doesn't exist yet and is probably at least 10 or 15 years away. But let's not get too discouraged. Smaller scale computations that are useful for chemistry simulation or optimization might need only hundreds of logical qubits with more modest error rates. And with a few thousand well-controlled physical qubits achieving gate fidelities around 99.5%, you might be able to do something genuinely useful in the next 5 to 10 years. So, let's think about what it would take to build, say, a 50 logical qubit quantum computer with the surface code. That might take somewhere between 5,000 and 25,000 physical qubits, depending on the code distance you use. You'd need all of those qubits on a chip, all connected in the right topology for the surface code, which requires nearest neighbor connectivity on a two-dimensional grid, which is actually one of the nicest things about the surface code from an engineering perspective. You'd need readout resonators and control lines for all of them. You'd need to get all those signals in and out of the dilution refrigerator. And you'd need to be able to do real-time classical processing of the syndrome measurement results fast enough to keep up with the error correction cycle. Let's think about the chip design challenge for something like 20,000 qubits. On a current generation chip, qubits are spaced something like a millimeter apart on the chip surface. Because each qubit has all its associated circuitry around it, the readout resonator, the coupling buses, the control line pads, the flux bias lines. A millimeter spacing on a 2 centimeter by 2 centimeter chip gives you a 400 qubit chip. To get to 20,000 qubits, you'd need either a much bigger chip or a way to pack qubits more densely, or multiple chips connected together. IBM and Google are both working on chiplet architectures where multiple smaller chips are assembled together. Google has demonstrated a 3-dimensional integration approach where they stack chips and use tiny indium bump bonds to make electrical connections between layers, which lets them put qubits on one layer and readout resonators on another layer and potentially fold up the chip footprint. IBM has their own approach using modules connected by cryo-CMOS electronics developed at cryogenic temperatures. There's an enormous amount of innovation happening in this area right now. And even if you solve the chip problem, there's the wiring problem. 20,000 qubits might need 60,000 or more individual wires going into the refrigerator, counting control lines, flux lines, and readout lines. That's an enormous number of cables, and each one carries some heat into the cold stage. Beyond a certain point, you just can't keep the thing cold enough with that many thermal loads coming from the wires. The solution is to develop multiplexed readout, where you can read many qubits through a single line by encoding each one at a different frequency. And for control, you want to develop cryo-CMOS logic that can live at temperatures of 4 Kelvin or below inside the fridge, close to the qubits, and accept simple digital commands from the room temperature controller rather than full analog microwave waveforms. Cryo-CMOS is a huge area of research and investment right now. Silicon transistors actually work at cryogenic temperatures, and in many ways they work better, with lower noise and faster speeds. But the design rules change quite a bit from what they are at room temperature, and there's a lot of work to be done on characterizing and modeling transistor behavior at low temperatures, and developing process design kits that chip designers can use to build cryo-CMOS circuits reliably. But let's zoom out a little bit and think about the software stack, because building the hardware is only half the problem. You also need to be able to program the thing. The programming model for a quantum computer works in layers of abstraction. At the very bottom layer is the physical hardware, the qubits with their resonance frequencies, their T1 and T2 times their connectivity graph, showing which qubits are coupled to which. At the next layer up is what you might call the calibration layer, the pulse shapes and durations for each gate on each qubit, the crosstalk matrices showing how driving one qubit affects its neighbors, the readout characterization. This layer is specific to the particular chip and changes over time as the chip drifts and ages. Above that, you have the circuit layer, where quantum algorithms are expressed as sequences of quantum gates applied to qubits. You might say, apply a Hadamard gate to qubit 3, then a CNOT gate between qubit 3 and qubit 7, then measure qubit 7. But you can't just send those instructions directly to the hardware, because the hardware only knows about specific microwave pulses. You need something called a compiler that translates the high-level circuit into the right sequence of pulses. The compiler has to solve several problems. First, if the algorithm requires applying a gate between two qubits that aren't directly coupled on the chip, you need to use a sequence of swap operations to move the quantum information around so it ends up on qubits that are coupled. This routing problem is NP hard in general and is an area of significant algorithm research. Second, the compiler needs to decompose any arbitrary gate into the native gate set of the hardware, which typically includes single qubit rotations and a 2-qubit entangling gate like CNOT or CZ. Third, it needs to schedule the gates to avoid conflicts and to take advantage of available parallelism, applying gates in parallel where the qubits involved don't overlap. The open source framework Qiskit, developed by IBM, has become a kind of standard programming interface for superconducting quantum computers. Qiskit lets you describe quantum circuits at a high level using Python, compile them to specific hardware targets, run them on simulators or on real hardware accessed via the cloud, and analyze the results. Google has Cirq, which is similar. There are also various other frameworks and languages for quantum programming. And above the circuit layer, you have quantum algorithm libraries that implement specific algorithms like quantum Fourier transform or quantum phase estimation as reusable subroutines. And above that, you have application level libraries that solve specific problems in chemistry or optimization or machine learning using quantum algorithms as subroutines. The quantum algorithm landscape is actually not as mature as the hardware side in some ways. We have a relatively small collection of quantum algorithms that are known to offer a genuine speedup over the best known classical algorithms. Shor's algorithm for integer factorization and the discrete logarithm problem, Grover's algorithm for searching unstructured databases, the Harrow-Hassidim-Lloyd algorithm for solving certain systems of linear equations, algorithms for simulating quantum systems. These are the canonical examples. But translating these into algorithms that are practically useful on near-term hardware with limited coherence and qubit counts is an ongoing and very active area of research. There's a particular class of quantum algorithms called variational quantum algorithms, which are hybrid classical quantum approaches designed for near-term hardware. The idea is that you have a quantum circuit with a bunch of adjustable parameters, called a parameterized quantum circuit or a variational ansatz, and you use a classical optimizer to tune those parameters to minimize some cost function. The cost function is evaluated by running the quantum circuit and measuring the output. The quantum computer handles the part of the computation that's hard for classical computers, and the classical optimizer handles the optimization. Examples include the variational quantum eigensolver for chemistry simulations and the quantum approximate optimization algorithm for combinatorial optimization problems. Variational algorithms are appealing because they can work with shallow circuits that don't require as many gate operations, which helps because the coherence time limits how deep a circuit you can run before errors accumulate. But they also have their own challenges, particularly something called the barren plateau problem, where the optimization landscape becomes essentially flat for large circuits, making it very hard for the classical optimizer to find good parameter values. Okay, so let's bring everything together and think about what a complete system actually looks like. You have a chip somewhere between a centimeter and a few centimeters on a side, sitting at 15 millikelvin at the bottom of a dilution refrigerator. On the chip you have anywhere from dozens to hundreds to thousands of superconducting transmon qubits, each one a tiny circuit of niobium and aluminum etched on a silicon or sapphire wafer, each one containing a Josephson junction whose tunnel barrier is an aluminum oxide layer only 1 to 2 nanometers thick. Those qubits are coupled to readout resonators that let you measure their states by sending in a probe microwave tone and looking at the reflected or transmitted signal. They are coupled to each other through coupling buses or direct capacitive coupling that enables 2-qubit gate operations. They receive control signals through microwave drivelines that bring precisely shaped pulses from room temperature electronics down through carefully engineered wiring in the refrigerator. The output signals travel back up through circulators, through parametric amplifiers at the mixing chamber stage, through hemped amplifiers at the 4 Kelvin stage, and up to room temperature receivers. At room temperature, racks of microwave electronics, arbitrary waveform generators, mixers, local oscillators, analog to digital converters, and real-time signal processors sit and hum in air-conditioned server rooms. They're all locked to a common clock reference software running on classical computers, compiles quantum circuits into pulse sequences and sends them to the control electronics. Measurement results come back, get processed by a decoder if you're doing quantum error correction, and get used to make decisions about what to do next. And on top of all that hardware, software frameworks let researchers and eventually users program the quantum computer to run algorithms without needing to know all the underlying physics. You write Python code that describes a quantum circuit, you push a button, and your code runs on the hardware. The whole system, from the millikelvin chip to the room temperature electronics to the software stack, is an engineering marvel that draws on physics, electrical engineering, cryogenics, computer science, optics, microwave engineering, material science, and software engineering. Teams of dozens to hundreds of people are needed to build and maintain these systems at the frontier. Now, let's think about what you'd specifically do, step by step, if you were going to attempt to build even a modest version of such a system. Let's say you want to build a 5-qubit quantum processor, which would be roughly at the scale of IBM's very first publicly accessible quantum computers from around 2016. 5 qubits is small enough to be simulated completely on a classical computer, so you won't be doing anything that a classical computer can't do. But it's large enough to demonstrate all the key concepts and to gain real experience with every part of the system. You'd start by reviewing the relevant literature, reading papers from the Yale group, the groups at MIT and Caltech and UCSB, from Delft, from Google and IBM, understanding the Transmon design in detail, the dispersive readout scheme, the cross-resonance gate, the calibration procedures. This literature review phase might take several months if you're coming in without prior background in superconducting circuit, QED. While you're learning, you'd also be designing your chip. You'd use electromagnetic simulation software like SONET or HFSS, High Frequency Structure Simulator, to design the resonators and couplers, getting the frequencies right and the coupling strengths right by adjusting the geometry. You design the qubit structures with target Josephson junction parameters and shunting capacitances to hit the frequency and anharmonicity you want. You'd lay out the whole chip, making sure control lines don't cross each other unnecessarily and ground planes are continuous. You'd simulate the whole thing to make sure everything looks good before you ever go near the clean room. Then you'd get access to a clean room. Academic physics and engineering departments at research universities have shared clean room facilities that qualified researchers can use. Getting qualified and trained to use all the equipment might take months of work alongside an experienced researcher. The critical piece of equipment is the electron beam lithography system for making the Josephson junctions, and these machines are expensive and in high demand, so you'd need to schedule time carefully. You'd buy your substrates, probably silicon or sapphire wafers from a supplier. You'd do the cleaning steps. You'd do the niobium deposition via sputtering. You'd do the photolithography and etch for the main circuit. And then you'd spend a long time getting the electron beam lithography and junction evaporation right. This part takes the most iterations. Your first few chips would probably be garbage, with junctions that don't have the right resistance, or that have shorts, or that the whole process is just slightly off and the qubits come out at the wrong frequency. You iterate. You change the oxidation time. You change the beam current. You refine the resist processing. Maybe after a few dozen chip runs, you start getting junctions with the right resistance within 10 or 20%. Then you'd need to test your chips, which requires cryogenic equipment. At minimum, you'd want a cryoprobe station that can cool a chip to 4 Kelvin in liquid helium, which lets you verify that the niobium is superconducting and that the basic resonators work. But for full qubit characterization, you need to go colder, and that means a dilution refrigerator. This is by far the most expensive piece of equipment in the whole stack. If you're at a university, you might share one with the group. If you're starting fresh, you're looking at a minimum of about $500,000 just for the fridge, plus the infrastructure to run it, clean helium gas, compressors, vibration isolation, electromagnetic shielding. So you'd work with what's available and start characterizing chips. You'd find that some qubits work and some don't. Maybe a Josephson junction on one qubit has a void or a short, and that qubit doesn't behave right. Maybe the readout resonator for another qubit has too much loss because of surface contamination you didn't remove in the cleaning steps. Each problem you encounter teaches you something and feeds back into improving your process. At the same time, you'd be building the control electronics. For 5 qubits, you need 5 control lines and 5 readout lines. You can use commercial microwave signal generators and spectrum analyzers for the initial characterization. For running actual gate sequences, you'd ideally use a reconfigurable instrument like a Keysight or Zurich Instruments AWG, arbitrary waveform generator that can produce complex pulse sequences under software control. The software framework for running experiments might be custom built in Python, or you might use an open source framework like QCodeDS, Quantum Computing Datasets, or Labber or RTIQ, which are software frameworks developed by the community for exactly this kind of experiment. You'd spend a lot of time at the experimental cycle of characterize, identify a problem, understand its cause, modify the chip design or fabrication or control approach, fabricate a new chip, characterize again. This is the actual day-to-day life of quantum hardware research, and it's a lot of patient, careful, often frustrating work, punctuated by moments of real breakthrough when something finally works as it should. Gradually, over time, the chips get better, the coherence times improve, the gate fidelities improve, the readout fidelity improves. You add more qubits, you add error correction, you add the decoder, you add the real-time feedback loop that lets you do active error correction in real time. At each scale, there are new challenges that you didn't have at smaller scale with 5 qubits. You worry mostly about individual qubit quality. With 50 qubits, you start worrying about frequency crowding, the fact that with many qubits at different frequencies, you might accidentally have some of them too close to each other in frequency, causing crosstalk. With 500 qubits, you're battling the wiring problem and worrying about the coherence of the chip-to-chip connections. With 5,000 qubits, you're thinking about the fault-tolerant architecture and whether your decoder is fast enough. These are the problems that Google and IBM and IonQ and Quantinuum and a dozen other companies are working on right now. Some of them with hundreds of engineers and scientists and billions of dollars in resources. And they're making real progress. In the last decade, qubit coherence times have improved by 2 orders of magnitude. Gate fidelities have improved from somewhere around 90% to 99.5% for 2-qubit gates on the best systems. Qubit counts on single chips have gone from a handful to over 1,000. Error correction below the fault-tolerant threshold has been demonstrated. The trajectory is genuinely impressive. And the beautiful thing is that all of this started from some theoretical ideas about quantum mechanics written down by people like Feynman and Deutsch and Shor and Grover in the 80s and 90s, before anyone had demonstrated a single qubit at all. The path from those theoretical ideas to the first superconducting qubit demonstrated by Nakamura and Tsai at NEC in Japan in 1999, to the Transmon qubit developed at Yale in 2007, to Google's demonstration of quantum advantage in 2019, to the below threshold error correction demonstrated in 2024, is one of the most remarkable stories in the history of technology. And the path from here to a large-scale, fault-tolerant, practically useful quantum computer is still long and hard. There are probably still unknown unknowns out there, problems that nobody has run into yet because nobody has tried to build systems at that scale. There might be new physics that shows up when you have thousands of coupled superconducting qubits in a single refrigerator. There might be decoherence mechanisms that nobody has characterized yet because they only become relevant at very long circuit depths. But the fundamental ideas are solid. Qubits exist and can be controlled with remarkable precision. Quantum gates work. Quantum error correction works. The Transmon qubit is a real manufacturable thing, and the processes for making it have been refined over decades of work. The dilution refrigerator is a mature technology. The microwave control electronics work. The software frameworks exist. What it takes, what it has always taken in the history of building new kinds of computers, is time, persistence, enormous amounts of careful engineering, and a community of researchers who are genuinely in love with the problem and keep coming back to it day after day, even when things don't work. And maybe it also helps sometimes to sit down somewhere comfortable, put on a long, slow explanation of how the whole thing works from bottom to top, and just let it all wash over you, thinking about the absurdity and the beauty of it. A machine made of quantum mechanics, a machine that holds superposition and entanglement in its hands. A machine cooled to a temperature colder than the universe, controlled by microwave photons, programmed in Python, slowly getting better and better, year by year, chip by chip, qubit by qubit. The Josephson junction is 1 to 2 nanometers thick. The tunnel barrier is 7 atoms of aluminum oxide. The qubit oscillates at 5 gigahertz, 5 billion times per second, in a state that is simultaneously 0 and 1, and the whole machine hums quietly in a dilution refrigerator somewhere, colder than everything, getting ready for whatever we're going to ask it to do. There is one more thing worth sitting with before we close, which is the question of what we're actually going to use these machines for once we build them, and why it matters. The most commonly cited application is chemistry simulation, and it's worth taking a minute to understand why quantum computers are especially suited to this. When chemists want to understand how a drug molecule works, or why a catalyst speeds up a reaction, or what the electronic structure of a complicated material is, they need to solve what's called the Schrödinger equation for the electronic structure of the molecule. This is a quantum mechanical equation that describes how electrons distribute themselves around the nuclei of the atoms in the molecule, and the solutions of this equation tell you the energy of every possible arrangement of the electrons, which in turn tells you the shape of the molecule, its reactivity, its optical properties, basically everything you might want to know about it. The problem is that the Schrödinger equation for a molecule with many electrons has to track a quantum state that lives in a space whose size grows exponentially with the number of electrons. For a molecule with 10 electrons, the state space has roughly 1,000 dimensions. For a molecule with 30 electrons, about 1 billion. For a molecule with 60 electrons, a number so large that no classical computer in existence could represent the full state, let alone evolve it in time. Classical chemists have developed incredibly clever approximation methods like density functional theory and coupled cluster methods that can get pretty good answers for many molecules without having to represent the full exponential state space. These methods are used to design everything from pharmaceutical drugs to batteries to semiconductors. But they fail for certain classes of molecules, particularly those with strongly correlated electrons, where the simple approximations break down. Transition metal complexes, which are important in biological enzymes and industrial catalysts, are notoriously hard to simulate accurately with classical methods. Nitrogenase, the enzyme that bacteria use to fix atmospheric nitrogen into ammonia, contains a complicated iron-molybdenum cluster at its active site that has resisted accurate classical simulation for decades. Understanding this enzyme fully could point toward ways to make nitrogen fixation less energy intensive, which would have enormous agricultural and environmental implications. A quantum computer could, in principle, simulate this kind of molecule with complete accuracy, because its quantum states naturally encode the full exponential state space without needing to approximate. This is exactly the application Feynman had in mind when he first proposed the quantum computer idea, and it's not just hypothetical. Researchers at Google and in various academic groups have already run proof of concept quantum chemistry simulations on current quantum hardware, simulating the electronic structure of small molecules like hydrogen, lithium hydride, and sodium hydroxide, using techniques like the variational quantum eigensolver. These are small molecules that classical computers can also handle easily, so the quantum computation isn't providing any advantage yet, but the methodology is being developed and tested so that it'll be ready when the hardware scales up. Another major application area is optimization. There are enormous numbers of important real-world problems that can be framed as optimization problems. Finding the best route for a delivery truck through a city, allocating financial resources in a portfolio to maximize returns, scheduling jobs on industrial machinery to minimize idle time, designing protein sequences that fold into a specific shape. These problems have an exponentially large space of possible solutions, and the best classical algorithms can often find very good solutions, but not necessarily the optimal one. Quantum algorithms might be able to search this solution space more efficiently using quantum interference effects. The Quantum Approximate Optimization Algorithm, QAOA, is one approach people have proposed for optimization problems. The idea is that you encode the problem in the energy landscape of a quantum system and then use a quantum circuit to try to find the ground state of that landscape, which corresponds to the optimal solution. There's significant debate about how large an advantage QOA can actually offer over the best classical algorithms for practical optimization problems, and this is an active research area. The honest answer is that we don't know yet whether quantum computers will provide a significant speed up for practical optimization, and it will probably take building the computers and running the experiments to find out. There's also quantum machine learning, which is probably the most hyped and most contested application area. Some researchers have proposed quantum algorithms that could speed up certain machine learning tasks, like training neural networks or running support vector machines. But there are also serious theoretical arguments that these speedups might not be as large as claimed or might not apply to the kinds of data that machine learning practitioners actually deal with. The field is young enough that it's genuinely hard to know what the eventual outcome will be. And then there's cryptography. Shor's algorithm, if it can be run on a large enough fault-tolerant quantum computer, would be able to factor large integers in polynomial time, which would break RSA encryption and most of the public key cryptography that the internet currently runs on. This is why there's an enormous amount of work happening right now on post-quantum cryptography, which is classical cryptographic algorithms based on mathematical problems that are believed to be hard even for quantum computers. The US National Institute of Standards and Technology has been running a multi-year competition to standardize post-quantum cryptographic algorithms, and in 2024, they announced the first set of standards. So, the cryptographic transition is already underway, even though the quantum computer that would break current encryption doesn't exist yet. This is the right approach. You start preparing for the threat before it materializes, because it takes years to transition cryptographic infrastructure. None of this tells you exactly when a practically useful quantum computer will exist. Predictions about this have repeatedly been too optimistic. People in the early 2000s were saying quantum computers would exist in 10 years. People in 2015 were saying 5 to 10 years. The honest answer is that we don't know. The hardware is getting better faster than many people expected in some dimensions, like coherence times and gate fidelities, and getting better slower than people expected in other dimensions. Like the absolute number of logical qubits that can be operated simultaneously, the error correction overhead is larger than people initially hoped. The classical control problem is harder than it seemed. The actual useful algorithms for near-term hardware are harder to develop than theorists predicted, but the progress is real and the direction is clear. And that's actually what makes this field so compelling to follow. You can watch in real time the gradual emergence of a genuinely new kind of computing, one that works on completely different principles from anything that came before. The history of computers is mostly a history of doing the same thing faster and cheaper. More transistors per chip, higher clock speeds, better memory, faster networks. Quantum computing is something actually different. It's a fundamentally different way of processing information, and we're watching it being built from the ground up. And that's really the whole thing. We went from a bare silicon wafer all the way to a working quantum computer. Through the clean room and the electron beam lithography and the Josephson junctions and the dilution refrigerator and the parametric amplifiers and the surface code and the compiler and the algorithm. The whole stack, from 7 atoms of aluminum oxide up to Python code running in the cloud. And if you're still here, hopefully some of it stuck. And if you drifted off somewhere around the dilution refrigerator, that's completely fine too. The quantum computer will still be there when you wake up, sitting at 15 millikelvin, colder than the universe, the niobium unmoved, the junction barrier still intact, the qubit still oscillating at 5 gigahertz, waiting for the next pulse. It is strange, and it is beautiful, and it is very slowly, very carefully coming to life. Good night.